Our project is Telesurgery Robot Control. I am Rebecca Jewell.
I'm Olivia Epler.
And I'm Caitlin Sangenberger.
Surgery is an extremely important practice that requires careful control of both the tools and instruments in order to perform operations without harming the patient. Remote surgery, otherwise known as telesurgery, is when a surgeon is not physically present while operating on the patient. The surgeon manipulates a robot at a distance in order to perform the surgery. When performing these operations by hand, human errors can lead to fatal mistakes, and surgeries can become more safer with robotic aid.
To model our system, we used a circuit that was connected to a motor, and the motor will output the voltage of the circuit, will input voltage into the motor, which will turn the tool that is used for surgery. We decided to model our surgical tool using a moment of an inertia and also a damper, which would model the tool going through tissue. And then we used algebra to just find our input, the theta, and then the voltage. And then we multiplied our angular displacement transfer function by s to find the angular velocity. The goals of our system were to be very precise, to be very accurate, and to have a fast response time. All three things are important in surgical operations.
So first we wanted to put our system into an open loop Simulink model. So once we included values into our original transfer function, that is what our model looked like in Simulink, and a corresponding angular displacement plot for the step response. In turn, we also plotted the root locus for the angular displacement step response, and it is good to note that the slope of our angular displacement step response matches the step response given in the prompt, and the angular velocity step response and root locus for the angular velocity are shown here, and the settling time for the angular velocity is about 0.7 seconds. The rise time is about 0.08 seconds with a percent overshoot of 44%. And so these are all values that could be improved with a controller. Finally, the Nyquist diagram showed on the right shows that this system would be stable in closed loop.
So the general characteristics of the angular displacement step response were acceptable for what our system is. If there's the velocity, the voltage will, a voltage input will give a velocity and angular displacement, and that relationship is linear. So if the voltage increases by a certain amount, the angular displacement will also increase by a certain amount. However, the angular velocity had a settling time and percent overshoot that were too high for our application, since we wanted it to be very precise and fast responding without a lot of error. So for our analysis, we decided to decrease the settling time and percent overshoot, and also to minimize the steady state error. So the specifications we decided on were a settling time of 0.5 seconds, a percent overshoot of 15%, and a steady state error of 0%.
So we used various aspects of MATLAB and the CISO tool to determine the values for our controller. So we used the desired percent overshoot to calculate a zeta value of 0.5169. Then this zeta value and the desired settling time of 0.5 seconds was used to calculate the natural frequency, which would in turn be the crossover frequency on our Bode plot diagram, and that was 17.798 radians per second. Finally, zeta would be used to calculate a minimum phase margin necessary to meet the design specifications, which was 51.69 degrees. In this, when the the crossover frequency was 17.798 radians per second, it is important that the phase margin was at least 51.69 degrees in order to meet our design specifications, which it was. As just described, here is the Bode plot used through CISO tool, and you can see that there is a frequency of 21.7 radians per second. The phase margin is 54.2 degrees and increases as the frequency decreases, so clearly those design specifications would be met. Still using that tool, a root locus plot was made with a 0 at the magnitude of the crossover frequency of about 17.8. And finally, here was the step response using that tool and our initial controller through CISO tool.
The controller for the system was a PD controller. Since there was already an integrator in the original transfer function, one was not needed to be added. The controller was designed using CISO tool, taking those 3 design specifications into account, the settling time, the percent overshoot, and the steady state or error. From that, we found that our controller was 0.9763s plus 17.434. For the closed loop stability, we looked at the Nyquist diagram, and as you can see, there are no encirclements around -1, leading to a stable. And with the root locus, there also was the no right-hand zeros. And so with that value equal to 0, as you can see in the bottom, all values were equal to 0, leading to a 0 stable closed loop. For verification, after designing our controller, we took the initial transfer function and modeled it in Simulink, added in the controller, and used the scope tool to plot the corresponding step response. As you can see in the plot, this step response is very similar to the response we found using the CISO tool. For the robust analysis, we looked at the gain and phase margins. The plot on the left is the original transfer function, while the plot on the right is for the transfer function with the controller. As you can see, there is a 41.5 degree increase in the phase margin and a 6.7 decibel increase in the gain margin.
In conclusion, the plant was stable with the addition of the controller. Specifications regarding steady state error, settling time, and the percent overshoot were all met successfully. And with these specifications, the telesurgery robot should function by the goals stated.